So last time we looked at graphing an object that was moving at a uniform velocity. Now let's look at graphing with acceleration. Okay, let's look at graphing with acceleration. And first, let's talk a little bit about what acceleration actually means. All right, we've defined what it is mathematically. It's the change in velocity over the change in time, but I want to try and give you a bit of a more concrete sense of what this actually means. Okay, so let's just look at a particular example. Let's just say that an object has an acceleration of 1 meter per second squared. All right, I want to try and give some concrete meaning to what this means. So assume that the object starts from rest. Okay, so if the object starts from rest, after 1 second of this acceleration, it will be moving at 1 meter per second. Okay, after 2 seconds, it'll be moving 2 meters per second. After 3 seconds, it'll be moving 3 meters per second, and so on and so forth. Okay, if the acceleration were not 1, but instead, let's say the acceleration were 5 meters per second, right, then these values would also change. Okay, so again, if it starts from rest, after 1 second, then the object will be going 5 meters per second. After 2 seconds, it'll be going 10 meters per second. And after 3 seconds, it'll be going 15 meters per second. So what the acceleration means is that the velocity is constantly increasing at this rate per second. Okay, so it's just going to get that much larger in each incremental change of time. Okay, so let's look now and see how we can use graphing with acceleration to determine some things about the nature of the motion of an object. So let's make another chart, and let's now say that we know that the acceleration of an object is fixed at a value of, let's say, 4 meters per second squared. Right? And let's do the same thing we did last time. Actually, and in this case, let's not use distance, but let's look at velocity. Okay, so at t equals 0, and if our initial velocity is 0, then at time 0, our object hasn't started moving yet, so its velocity will be 0. After 1 second, okay, then its velocity is going to be 4 meters per second, and we can get this. Okay, I'll go ahead and give you the general formula. We've seen it before, but I'll derive it for you again. Remember that acceleration is equal to Vf minus Vi over t. Okay, and so what we're wanting to do is solve for the final velocity of an object if we know what its initial velocity and its acceleration is. And so we want to solve for Vf here. And what I can do, well, I've already done it before, so I won't do it all over again. I'll just give you the main result. And we have Vf equals Vi plus At. Okay, I can also write this as At plus Vi. Okay, either way, it's addition, so 2 plus 3 is the same thing as 3 plus 2. It doesn't matter. And so I'm getting these final velocities over here. So Vf is going to equal 4 meters per second squared times 1 second, and that gives me 4 seconds, meters per second, sorry. Again, this is going to be in seconds, and this is going to be in meters per second, right? So this is meters per second. And after 2 seconds, right, after 2 seconds, then I'm going to be traveling at 8 meters per second. And after 3 seconds, I'll be traveling 12. Okay, so we have this data, and first things first, let's go ahead and plot it. All right, so let me go ahead and erase as much of this as possible very quickly. And we'll make a small plot and see what it's telling us. All right, that's good. And we'll put time in seconds over here and velocity in meters per second here. Okay, so we'll mark off some time ticks and we'll mark off some velocity ticks. Okay, so our equation starts at the origin, and after 1 second, we're going 4, after 2 seconds we're going 8, and after 3 seconds we're going 12. And it looks like, again, we have another straight line, which is in fact what we do have. Let me make these just a little bit bigger so that they all fall on the line. And what we can see now is that the slope here again has an interpretation, okay? And if we calculate the slope, if I take the rise over the run between any 2 points, I see that there's a rise here of 4 meters per second and a run of 1 second, and so the slope is going to be 4 meters per second squared. So the bottom line here is that for an accelerator or a velocity versus time, the slope is the acceleration. Okay, so for a velocity versus time graph, the slope is the acceleration. Okay, and now that we have that, let's look at one more thing that will also help us to look at how the distance of this object is moving. Okay, so I'm going to erase all of this again, unfortunately, but I'm going to make an extension of this data table, which is why I don't want to draw it again. All right. Now, first things first, go back to the formula for distance. Remember that distance equals velocity times time, but that velocity was the average velocity. Okay, that velocity was the average velocity. So, what we want to do is calculate the average velocity in between each time interval, and then calculate the distance that goes along with that average as well. Right? So in the first time interval, our velocity started at 0 and then went up to 4. And if we take the average of these two velocities, okay, 0 and 4, the average is going to be 2. So in the first second, okay, remember that d equals vt, where v is average velocity, okay? So if d equals vt, then at 1 second, velocity, an average velocity of 2 meters per second times 1 second, it will have traveled 2 meters, okay? The next increment, okay, the average of 4 and 8 is going to be 6, and 6 times 2 is going to be 12, And in the next increment, the average of 8 and 12 is 10. And the velocity times the time, 8 times 3, or I'm sorry, 10 times 3 is going to be 30. So after the first second, it covered 2 meters. After 2 seconds, it covered 12 meters. And after 3 seconds, it covered 30 meters. Okay? So notice that each increment of time, the object covers more and more distance. Okay? So distance does not increase uniformly with time for an object that's accelerating, which that makes some sense. And I just told you wrong about a couple of things, so let me go back and correct those. The first calculation is correct, okay? Now, the distance over here, the total distance that the object is going to move, okay, needs to be not calculated at each incremental second intervals, but over the course of the entire trip. So for our second distance right here, okay, instead of looking at the velocities from 4 to 8, I need to consider from 0 to 8. Okay, so the average of 0 and 8, okay, is 4. So this velocity should actually be 4. So 4 times 2 should actually be 8 over here. Okay, and then from 0 to 12, the average is not 10. That average is 6. And so over the course of 3 seconds, from 0 to 3, if the average velocity was 6 seconds or 6 meters per second over those 3 seconds, then 6 times 3 should actually be 18. Okay, but the relationship that we saw before, the general trend that we saw before, is still true. Okay, these do not increase uniformly in each increment of time. Now, how can we get a formula that relates acceleration and distance? Okay, well, remember that acceleration is equal to v over t, or change in v over t, and distance is equal to the average velocity. I'll use a bar for average, okay? So average velocity times time. Now, how can we marry these two equations together, right? How can we marry these two equations together? Well, the key is to notice that the change in velocity is going to equal 1/2 the average velocity. Okay? Or actually, I have that backwards now that I'm thinking about it. The average velocity is going to equal 1/2 the change in velocity. Okay? And again, this goes back to what we were just doing. If an object starts at 0 meters per second, and let's say 1 second later it's going 4 meters per second, then the average, if I average those two out, it will be 2 meters per second. And 2 is just 1/2 of 4. So my change in velocity from 4 to 0, 4 minus 0, 1/2 of that is 2. So my average velocity is 1/2 my change in velocity. Okay? And so what we have now, what we can do, is look at this equation right here and solve it for delta V. And we'll have delta V is equal to AT. But delta V in this equation can now be replaced by the delta V here. So the average velocity equals 1/2 the acceleration times the time. Okay, so I'm just basically taking these values and plugging them up into here because our delta v's are equal. And the bottom line is now that I can plug this expression into this expression. And when I do so, I'm going to get d is equal to 1/2 at times t, right? So my average velocity is 1/2 at, and it's multiplied by another t. So 1/2 at is my average velocity times time. And when I multiply all this out, I'm going to get 1/2 at squared. Okay? And this is why the distance does not increase uniformly with time under constant acceleration, because as the time goes up, the distance goes up quadratically or squared with the time. So under constant acceleration, if I graph distance versus time, okay, then because this is squared, my object will not be, my line will not be a straight line. Okay, it will not be a straight line. It will actually be a parabola. If you go back to your graphing from algebra, you'll remember that y equals ax squared is a parabola. And it looks something like this, right? It curves and then shoots upward, right? Now, this is going to be an extremely important formula going down the road, right? D equals 1/2 at squared. And this was assuming, okay, again, this was under the condition of constant A, but this was also assuming that VI equals 0, okay? If there was an initial velocity, if it doesn't equal 0, then we can modify the equation to read D equals VIT plus 1/2 AT squared. All right? So this is the formula that relates velocities, initial velocities, distances, accelerations, and times. Okay? So now let's recap all of the equations we have so far. We call these our kinematic equations. Okay? So we have let's say velocity equals average velocity equals distance over time. And then we have acceleration is equal to change in velocity over time. We have the final velocity of an object can be found if the initial velocity is known, and we know the acceleration and the time. And then we also have the distance equals VIT plus 1/2 AT squared. Okay, so these are all the equations we've built up so far. I highly encourage you to keep these in a quote-unquote equation library that you can have for quick access. And the next short video, I'll just go through a couple examples of how to algebraically manipulate the distance equals VIT plus 1/2 AT squared equation. All right, so we'll just do a couple quick examples in the next video. All right, we'll see you then.